Hello and welcome to yet another video of Cornerstones of Math. I plan to upload sequence problems from time to time, and today we deal with relatively simple yet important property of sequences. Here, for a sequence whose nth term is an, its partial sum, the sum of first n terms of the sequence, is given and denoted as Sn. And we have to find the nth term an from the partial sum Sn. In the first problem, the partial sum Sn is given as n squared plus 3n for all natural numbers n. And in the second problem, Sn is given as n squared plus 3n plus 2 for all natural numbers n. We'll see how this tiny difference affects our answers in an interesting way very soon. So let us start with the first problem. The trick is simple. The partial sum Sn is a1 plus a2 plus so on plus an-1 plus the last term an. Here, the sum of first n-1 terms can be written as Sn-1, and this means that an is Sn minus Sn-1. Here, n is greater than or equal to 2 because these Sn's are only defined for natural numbers n, so Sn-1 cannot be defined when n equals 1. This will come important later, but for now, let us actually apply this formula to our given Sn. So when n is greater than or equal to 2, an is Sn minus Sn-1, which is Sn is n squared plus 3n, and Sn-1 is n-1 squared plus 3n-1. So we have n squared plus 3n minus n squared minus 2n plus 1 plus 3n minus 3. So n squared plus 3n minus n squared plus n minus 2, which is 2n plus 2. Here, this n is greater than or equal to 2 condition still applies. Then how do we find the first term a1? Well, we use the fact that a1 is just s1 because the sum of first one term is, just the first term itself. And it is given that the expression for Sn holds for all natural numbers n. So we simply substitute n equals 1 in this expression to obtain 1 squared plus 3 times 1, which is 4. Now notice that this expression, 2n plus 2, also gives the same result when n equals 1. Therefore, for this particular problem, we can say that the expression 1 also holds for n equals 1. Therefore, we can write our answer as an equals 2n plus 2 for all natural numbers n. Now, if you plug in some numbers to obtain first few terms, you'll notice that an is an arithmetic progression with a common difference of 2. You can also verify that an is an arithmetic progression by using this result and showing that an plus 1 minus an equals 2 for all natural numbers n. Alright, now let's move on to the second problem. Here, Sn can be factored into n plus 1 times n plus 2, and using this factored form is just a bit simpler. So we do the same thing. When n is greater than or equal to 2, an is Sn minus Sn-1, which is n plus 1, n plus 2 minus, and this part must be n plus 1. So n plus 1 is a common factor, and we have n plus 2 minus n. So we have 2n plus 2. So we have obtained the same expression, but here comes the difference. Since this only applies when n is greater than or equal to 2, let us find our a1 separately by a1 equals s1. And using this given expression, we have s1 equals 6, which is not the same result when we substitute n equals 1 into here. Therefore, this expression, obtained by Sn minus Sn-1, does not hold when n equals 1. Therefore, we must write the answer as the first term a1 is 6 and an is 2n plus 2 when n is 2, 3, 4, and so on. And if we obtain first few terms again, you'll notice that an is an arithmetic progression except the first term. That is, it is an arithmetic progression from the second term and onward. This difference occurs because in this problem, Sn is defined prior to An. You see, I will not stray too far in this video, but if you add up the terms of the arithmetic progression, the strict arithmetic progression right from the first term, then the partial sum is always given in the form of Pn squared plus Qn. That is, a quadratic polynomial with zero constant term. Therefore, if you are a math teacher and you want to put similar problem in the test where the answer is just a simple arithmetic progression, without any sneaky trap like this problem, then just making Sn a quadratic polynomial isn't enough. You have to make sure that the constant term is 0. Still, we deal with a whole lot of other sequences other than simple normal arithmetic progressions. So let us remember that our useful property Sn minus Sn minus 1 only gives you the answer for n greater than or equal to 2, and you have to obtain a1 separately from S1. And that's all for today's video. Please hit that like and subscribe buttons if you found this video helpful, and I will see you in another video.